Remember yesterday when we were talking about sets, we said that an empty set is a subset of every set. An empty set is a subset of every set. Then you remember an empty set is what we call the impossible event. So that is when we don't have any members. Okay, we don't have any members in that set. So we call that one an empty set, or in this case, we can say that it is an impossible event or a null event. Can someone give us an example? Let me say related to days where we don't have any day. Anything that is happening on a particular day, I don't know. Or any other example where we have an empty set. Can someone think about an empty set or an empty event? Hello?
Empty set, I think.
I was just trying to find out if someone can give us an example of an event which turns out to be an empty set. Or let me just give an example. You can have a set, let me say which, come again? Yes, please. You were giving us an example. Yes. So is that an empty set? Okay.
Yes, sir.
Very good. Let us have another example. Suppose we toss a die. I hope everybody knows a die. It has 6 sides. So every side has got a number of dots. There is a side which has 1 dot, a side which has 2, a side which has 3, then up to the side which has 6. So when you toss a die, the sample space has got 6 points. You can get a face which is having 1 dot. You can have a face having 2 dots, or a face having 3 dots, and so on. Because we have 6 faces. So if the die is fair, each of those ones is a chance. Each of those ones is a chance of showing up when you toss a die. So if now we talk again about 3 elements, event A is an event where an even number will appear. So what do we have in A?
We shall have 2, 4, and 6.
Very good. So event A will be having elements 2, 4, and 6. And you remember we write them as sets because these are subsets of a big set S. Now, event B is an event that an odd number will appear. So what do we have in set B?
Set B, we have 1, 3, and 5.
Set B?
We have 1, 3, and 5.
Very good. So set B will be having 1, 3, and 5. Then set C is an event that a prime number will appear. So what do we have in set C? One, 3, and 5. Now here we need to apply some mathematics. Is 1 a prime number? Are you sure? Well, I don't know, but in most cases, it is not taken as a prime number. How about 2? Is it a prime number?
I think no.
How do you define a prime number? How do you define a prime number?
Prime numbers are numbers which are divisible by themselves.
Okay. So, is 2 a prime number?
No, because you can divide it by 1. No. Yeah, pro is a prime number.
So by definition, 2 is both. It is an even number and it is also a prime number. But 1, we don't consider it as a prime number. So here, those are the sets we have. Set A, like we said, is a set of even numbers, which means that it is going to have elements 2, 4, and 6. Set B, a set of odd numbers. It will have 1, 3, and 5. Then set C, a set of prime numbers. It will have 2, 3, and 5. Okay? We continue?
Yeah, let's go on, sir.
Okay. So we can have set operations. For example, you can talk about A union C. You can talk about B intersection C. Or you can talk about A C complement. A union C, that is an event that you get an even number or a prime number. You get an even number or a prime number. Remember, if we are using the word or, that means a union. Then B intersection C, that means we are getting an odd number, which is also a prime number. An odd number, which is also a prime number. Then when we talk about C complement, that is an event where we don't have a prime number, an event which is not a prime number. Okay, so note that A and... Any question? So note that A and B are mutually exclusive. I think that is obvious. Remember we said mutually exclusive means that you don't have elements in common. So if A is a set of even numbers and B is a set of odd numbers, then it means you don't have elements in common. A number can't be both even and at the same time it is odd. So it means A and B are mutually exclusive, meaning that A intersection B is an empty set. Okay. Now, someone can say that you carry out an experiment, you toss a coin until a head appears, and then you record how many times did you toss before getting a head. Can someone tell us like an answer you can get? You toss, and then your interest in getting a head. Can you determine when the number of times you have to toss before getting a head?
So now there are 2 times.
How?
Because a coin has two sides. You either get a head or a tail.
Yeah, but what we are saying here is how many times do you have to toss before getting a head? So I can toss and I get a tail. Is that right? I can toss the second time, it also gives me a tail. I think that is possible.
Yes.
I can toss a third time and it also gives me a tail. So, so you are looking for a head. Are you sure how many times you will toss before getting a head?
No, sir.
I think it is not possible because you can get a head with only one toss. I can toss once and then I get a head. But I can toss twice, no head. 3 times, no head. 4 times, no head. It is possible. So the sample space of this experiment can be in a number 1, 2, 3, and so on. Because you are not very sure how many times you will toss before getting a head. So since every positive integer is possible, then we can say that that sample space is infinite. Okay, let us have another example. Let us now toss a pair of dice. A pair of dice. That means one die is 6 sides, another die is 6 sides. So does someone know the sample space? How many sample points you can have when you toss a die 2 times? No, when you toss 2 die. You first toss, you record what you have, and then you toss again, you record what you have. So how many different combinations can you have there? Hello?
I'm asking to a bit repeat
Yes, please.
because I'm not really clicking well.
So we are saying that you are tossing now 2 dice. Okay? Now each die is 6 faces. So you can, let me say you can toss the first die and maybe it shows a 1. Then the second die can also show a 1. So 1, 1 is 1 point, 1 possibility, meaning that the first die is a 1, the second die is a 1. Another point can be that when you toss, die number 1 shows a 1 on top, but die number 2 shows a 2. So that is another possibility. Or you can have, let me say you can toss, die number 1 who has a 3, and the die number 2 has a 5. So that is another possibility. So how many different points do you think can you have which make up this sample space?
I think there are 12.
Yes, please. Mm. Mm. Very good. So the total sample space is 36. The total sample space is 36. Because you can take, let us say die 1 is a 1, die 2 is a 1, that is 1. We can have a 1, 2, a 1, 3, a 1, 4, a 1, 5, a 1, 6. We can have a 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. You can have a 3, 1, 3, 2, and so on. So by the time you get to 66, I think you have a total of 36 points. So the sample space S consists of pairs of numbers from 1 to 6, which are 36. So if you look at that diagram there, it shows all the possible points which you can have. Maybe you can look at it. The first one, the first entry is the first die. The second entry is the second die. So you can see that you have a total of 36 different points. I am wondering if there is a question there.
I think we can go on.
Okay. Kindly, if there is something you don't get, don't hesitate to let me stop and explain more. I don't want to leave anybody behind. We don't have a lot of time. And you remember we have a test on Saturday next week. Okay? So if A is the event that the sum of two numbers is 6, can someone tell me the points which are in that set A, where the sum of the two numbers is 6? Can you guess or tell me what you may have in that event A?
Can I try?
Yes, please.
I think it is possible that we can have 4, 2.
Mm-hmm.
Then we can have 3, 3.
Mm-hmm.
It is possible that we can have 5, 1.
Mm-hmm.
We can have 2, 4.
Okay.
Yes, sir. I think those are the possible ways.
Now we can have more.
Okay.
There is one more which maybe is missing. What is missing?
Okay. I can repeat. I talked of 1, 5.
Okay, you had missed that one. You talked about 5-1.
Okay.
Okay. There is a 1-5. There is a 1-5 also. Mm.
Yes, sir.
Okay.
Okay.
So,
Okay, sir.
so that is what we have. So we have a 1-5, a 2-4, a 3-3, a 4-2, and then a 5-1. So that is event A, where the sum will be 6. Event B is that the largest of the two numbers is a 4. The largest of the two numbers is a 4. So what are you going to have there? You can have a 2-4. Now this is a different set B. It is not related to the first. We are looking at all the 36 possible points. So 2-4 is one of them, but there are so many others.
There is even 4-2.
There is also 4-2. I'm saying this one is not related to A, which is a sum of 6. This is a different event. Four one, 4-1, 4-1, 4-2, 4-2 was already mentioned. 4-3, and maybe 4-4. I think there is another one. I think you forgot a 1-4. Don't you think it is also there? Okay. So that one has got a 1-4, a 2-4, a 3-4, a 4-4, a 4-3, a 4-2, a 4-1. So that one, I think like you can see that is an event that when you toss a die, the biggest number is a 4. Okay. So you can talk about event A intersection B. That means that when you toss a die, the number is 6 and the biggest number is a 4. So when you look at those two sets, set A and set B, A intersection B will be having those ones. Okay. Then A union B will be having all those numbers which either the sum is 6 or the biggest number is a 4. Either the sum is 6 or the biggest number is 4. So when we look at this diagram here, I think you can see set A. I don't know if you can see set A. Set A is that one which has got like I don't know if you can identify it on the diagram. A 105, a 24, a 33, a 42, a 51. So that is a set which has numbers that when you add the two numbers, you get a 6. Then another set where set B, where you have a number that when you set B, that the biggest number is a 4. I think you can see that B, which is like a, is it like an arrow or what? Is it okay? Okay. So, and then you can see the intersection, a 4, 2 and a 2, 4. That is the intersection. I hope you can see that one also. Is it okay? You see those sets, those two sets? Okay. So that is what we are talking about. You see elements in set A, and you see elements in set B. And then you can see the intersection. And when you take everything, everything is the union. So long as a point is shaded, it lies in the shaded area, that is a union. Okay. Let us have another experiment. This is an experiment of cards, a deck of cards. I hope everybody has at one time or another played the cards. Now, like you know, a deck of her cards, he has got 52 cards. Now the cards, like you know, they have 4 suites. Some cards, we call them the clubs or flowers, they are 13. Then diamonds, they are also 13. Hearts, they are also 13. Spades, they are also 13, which makes a total of 52 cards. Each suite is 13 cards. Now, those cards, we have cards which have numbers. So some cards have numbers 2, 3, 4, 5, 6, 7, 8, and 9. 9 and 10. So those ones, we call them numbered cards. Then we have cards which have pictures. K, Q, the K, Q, and the J. I think K, we call it a king. Q, we call it a queen. J, we call it a jack. Those are picture cards. Then we have the S's. The A for the clubs, the A, the diamond, the A, the hearts, and the A, the spades. You know the clubs and the spades are black. The diamonds and the hearts are red. Okay, I think that is what you need to know about those cards. Well, we know all of that. Okay, now suppose someone asks you to find the members for event A, where the event A, that it is either a picture card or a face card. So what are you going to have in that set? A set which has got a picture card or a face card. The picture and the face, that is the same. It is a picture card, stroke of face card. So how many picture cards do you have in total? How many picture cards do you have in total? Are you sure? Are they 4 or each suite has 4 pictures? What are the 4 pictures? I think A is not a picture. Is it a picture card? No, I think that we don't consider that one as a picture card. The picture card, that one having bazungus, I think is K, Q, and a J. Those are the picture cards. Is that right? So we can talk about a club, a club which is a club, a king club, a queen club, a jack club, a king diamond, a queen diamond, a jack diamond, a king hat, a queen hat, a jack hat, and then a king spade, a queen spade, and a jack spade. So there we have, I think, 12. Then, if F is the event that a card is a heart, how many hearts do we have in total? How many hearts do we have? The total of hearts? Why do you subtract them? Why do you subtract the king, the queen, and the jack? They are also hearts. Because if we talk about the total for hearts, so how the total of hearts, there are how many hearts? 13. Yeah? So we can talk about the intersection. We can talk about the intersection. The intersection will be, because you remember we first said we take those cards which are pictures, and we said that we have a picture which is a picture which is a club, a picture which is a queen, a picture which is a jack. Then we have a picture diamond, a picture queen, a picture jack. Then we have a picture heart, a picture queen, a picture jack. Then we have a picture spade, a picture queen, sorry. Yeah, a king spade. We have a queen spade and a jack spade. So that is the set E, which is a set of pictures. I think you can see set E, that one, which is like a horizontal. That is the set for pictures. Then you can see set F, which is a set for hearts. That is the vertical set. So if you talk about E intersection F, meaning that you are looking for a card which is both a picture and it is also a heart. So we can say that we will have a king heart, a queen heart, and a jack heart. So that is the intersection. Is it fine? Are the other colleagues following? I want to hear the others also saying a yes or a no.
Somehow, sir.
No, I don't want the somehow. I want it very. Tell me you are very comfortable with it. Somehow you will get confused sometime in the future, and I don't want you to get into confusion.
The challenge, I got some network problem in the middle there. Then I went off. So I got.
Sorry. I don't know. Are they playing cards? I think those are not playing cards. We don't count them as playing cards. Yeah. The playing cards are those 52. Okay, let us continue. Now, let us try these questions. Let a coin and a die be tossed. We are tossing now a coin. We know it has 6 faces. A die has 2 faces. Can someone tell me the sample space? How many points, different sample points do we have in that sample space? There are 12. Can you list them? Okay. Very good. Very, very good. So that sample space is 12 sample points. Is that clear to everybody?
It's okay, sir. It's clear.
Okay. Then we can go to part B. Part B, can you tell me events or points which are in that for that event where you have heads and an even number? Heads and an even number. So what will you have there? Very good. We have a head 2, a head 4, and a head 6. How about B? Set B is a set where you find a prime number. Okay, I think that is also okay. Then part C where you have a tail and an odd number. A tail and an odd number. Very good. You people, are you listing those? Because the question is continuing for whatever we say. Their subsequent question is related to the previous answers. Have you been writing? So remember the sample space we said it has got 12 points. 1 head, 2 head, 3 head, 4 head, 5 head, 6 head. Then 1 tail, 2 tail, 3 tail, 4 tail, 5 tail, and 6 tail. So that was the sample point S. Then event A or set A is that event where you have a head and an even number. So we said we have 2 head, 4 head, and 6 head. Event B is where we talked about a prime number. So since we said 2 is a prime number, so we have 2 head, 3 head, 5 head, and a 2 tail, 3 tail, 5 tail. Then event C, tail and an odd number. We said we have tail 1, tail 3, and a tail 5. Eh? I think we are still continuing, by the way. Tail 1, tail 3, and and tail 5. I was going to say tail 7. No, because we have only 6 faces. Now we can go to part C. Can someone write members in that set A or B? When we say A or B, what do we mean as far as the sets are concerned?
I think that is the A union B.
Very, very good. So can we get members in A union B? Can someone let us know members in A union B, that is A or B? Yes, please. I think one we said is not a prime number. Yeah, one is not a prime number. So where you have a 1, prime numbers, we said for set B, we said you have 2 head, 3 head, 5 head, then 2 tail, 3 tail, and a 5 tail. So when you combine that one with the 2 head, 4 head, 6 head, I think that will give you A or B, that is A union B. Then B and C. So what do we mean there?
B and C, there we looking at B intersection C.
Okay. Do you know? Can you find out what is there in B intersection C? If you listed them, Yes, please. Maybe 3T and 5T. Let me see. And B we have. You said the T3 and the T5. Okay, then what do we have in only B? Only B. Three H and 5H. I think we are interested in finding those members which are only in B. And you don't have them in other sets. Did we have 3H anywhere? Okay, 3H and 5H. 2T is somewhere else. Yeah, I think it is a prime number. Yeah, T2 is a prime number. Is it somewhere else? It is not in C. And it is not in A. What do you think about that one? I think it qualifies, okay? Then which pairs are mutually exclusive? When we talk about pairs, you can take A and B, you can take A and C, you can take B and C. Which ones are mutually exclusive? That means which pairs don't have any intersection. You compare A and B, you can compare A and C, then you can compare B and C. And you can tell which ones don't have intersections. That's what we mean by mutually exclusive. I remember I asked you to write. It seems some colleagues have abandoned us. They have kept quiet. My request is let us all participate. I will try to be slow such that we move together. You feel we are leaving, you kindly stop us. I don't want to leave anybody behind.
So it's not that we have abandoned, but Somehow behind there I lost network. So as I was waiting maybe to get time and internalize slowly by slowly. Read the, my side.
Okay, so sorry about that.
So other than lagging you behind, I decided maybe I'll get time and then internalize, read back slowly by slowly.
Okay.
Yeah. But we are here, we are listening. However, I'm trying to pick. So once I'm back on board, I'm going to respond.
Okay.
Yes, sir.
Let me pray that you pick the sooner the better.
Okay, sir.
Okay. Have you found some pairs which are where you don't have any intersection?
So I'm trying to ask here.
Yes, please.
Are we still on the card thing? Oh, we are on the.
We have. Do you see the screen?
I'm seeing it.
Okay, so we are answering that question. That question has got. They are saying let a coin and a die be tossed.
Oh, so all along I was wondering how cards are having heads and tails. So,
so we are there. That is what we are doing.
Okay.
Yeah. So all these other questions are following from that statement above, that we are tossing a coin and a die.
Okay, sir.
Okay.
Maybe you can proceed. I'm going to pick because I was trying to add up because I'm seeing head and tail.
Okay.
As a question, but I went off when we on cards, so I was trying to add up how do cards have tails and so on. But now I'm on track.
Okay, please. Okay, so we are trying to do part D. Part D, that is where they are asking us to find which sets are mutually exclusive. And we define the mutually exclusive as those sets which don't have any members in common, where we say that the intersection of those sets is an empty set. So when you consider A and B, you remember A, we said A has got 2 head, 4 head, and 6 head, because they said we want a head and an even number. Then B is a prime number. Now a prime number, we said 2 is a prime, so we can have head 2 or 2 head and 2 tail. We said we can have 3 head and 3 tail. We said we can have 5 head, 5 head and 5 tail. Is that right? That was for B. Now, if you say that A and B are mutually exclusive, are you right? Don't you see any intersection there?
Head.
Between A and B. I think 2 head. It seems as if me, I wrote 2 head is appearing in both sets. 2 head is an even number, and the 2 head is also a prime number. So that means A and B are not mutually exclusive. So how about B and C? So we have tails and the odd number. So those ones, they are also having some elements in the intersection. Then we can think about A and C. I think A and C are mutually exclusive. We don't have any intersection there. Is that okay? Yeah, so that is the set which is mutually exclusive. Okay, let us continue. There is another question there. A pair of die is tossed. Find the number of elements in each of those sets. I would want you to list them even. Set A, two numbers are equal. You are tossing a pair of die. Event A is where two numbers are equal. So what do you have in set A?
Excuse me, sir.
Yes, please.
Two numbers are equal. I think I mentioned them or I just mentioned a number.
May I say that you want both? Maybe you first mention them, then we will count.
So you can have 1, 1.
Yes.
2, 2. 3, 3.
Yeah.
4, 4.
Yeah.
5, 5.
Yes.
Then 6, 6.
Very good. How many are they?
6 pairs.
6 points. Okay.
Yeah, 6 points.
Then
Yeah.
set B. Set B, the sum of the two numbers is 10.
Sum.
10 or more. They are saying 10 or more.
I think here we have 4, 6. We have 5, 6. We have 5, 5. We can have 6, 6.
Okay.
Yeah, I think there are only 4 pairs.
You forget a 64 and a 65?
Yes, 64 and 65, yes.
Okay, so how many do we have in total?
There are 6 pairs.
Okay. Then 5 appears on the first die. Five appears on the first die.
I think here we have 5-1.
Yes, please.
And 1-5.
5 appears on the first die.
We have 5-1 and 1-5.
No, 5 appears on the first die. So when you say 1-5, it means a 1 is on the first die.
Okay.
So what do we have on the first? 5 appears on the first die.
So we have 5-1.
Only? You are tossing a die 2 times.
I think we have 5-1, 5-2, 5-3, 5-4, 5-5, then 5-6.
I think that is it. Very good. So you can see a 5 is appearing on the first die for those 6 cases. 5-1, 5-2, 5-3, 5-4, 5-5, and 5-6. Then a 5 appears on at least 1 die.
At least on 1.
Yes.
I think we shall have at least on 1. We shall have 1-5, 2-5, 3-5, 4-5, 5-5, 6-5, then 5-1, 5-2, 5-3, 5-4, then 5-6.
Very good. Very good. I hope.
Yep.
I hope we can list those ones and then we can count how many they are. I hope you are getting the point, ladies and gentlemen. I don't want to leave anybody behind. Are we moving on together?
We are together now.
Okay. Okay, let us now talk about what we call a finite probability space. So we have already said that if we have a sample space, the sample space has got points which we can call point A1, A2, A3, up to whatever number it might be. You remember we said that is a what? A sample space. Now that we talk about a finite probability space, that is obtained if each of those points, like for example, when we talk about a die, it has got 6 points. Each of those points can be assigned a number which we call a probability of that point happening. A probability of that point happening. And that number has got 2 properties. First of all, it should be non-negative. That means the probability of that particular number should be greater than 0. That means it shouldn't be negative. And when you add up all the probabilities of each of those points, you get a 1. Like in the case where we have 6 points, the probability of having a 1 plus the probability of having a 2 plus the probability of having a 3, when you add up all those probabilities, the sum is a 1. So that is what we are talking about now. In a sample space, each point can be assigned a number which we call a probability, Pi. So Pi is the probability of a point, and it shouldn't be a negative. And then when you add up all the probabilities of all of the points in the space, it should sum up. It should sum up to a 1. Then the probability of an event is the sum of the probabilities of those points. Okay? Now, let me give an example. Again, you remember we started by considering the days when we have our mathematics lectures. Okay? So we have, let me say, 7 days in a week. So the probability of a Sunday is, we divide that one into 7 points. So the probability of, let me say, Sunday is 1/7. Probability of a Monday is 1/7. Probability of a Tuesday is 1/7, and so on. So when you add up all those probabilities for the 7 days, you will get a 1. And each one is greater than 0. So each one, like here we are saying, each day is 1/7. Now, when we take the days which we have mathematics, we said that is Thursday, Friday, and Saturday. So you can add the probability of Thursday is 1/7, plus the probability of Friday, we said that is also 1/7, plus the probability for Saturday, that is 1/7. So we get 3/7. That is the probability for the event when we have lectures. So that is what we mean, that the probability of an event, which we write as the probability of event A, is defined to be the sum of the probabilities of each of the points which are in that event. I don't know if it is clear. Okay, maybe we are going to get another example. Let us look at this example. Suppose 3 coins are tossed. So when you toss 3 coins, you remember the sample space we are getting. Head, 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 tail. The sample space was having 80 points. I hope you remember. So now you are interested in recording the number of heads. You are interested in recording the number of heads. So you can toss 3 times and you get 0 heads. That is a possibility. You can toss 3 times and you get only 1 head. You can toss 3 times and you can get 2 heads. Or you can toss 3 times and all the 3 times are heads. So the sample space for heads is that one. Either you don't have a head, or you have 1 head, or you have 2 heads, or you have 3 heads. So if you are interested in the sample space for heads, that's what you have. Now, the probability of getting, the probability of a 0, the probability of 0 heads is 1/8. I don't know if that is obvious, because of all of the 80 sample spaces, it is only tail where we don't have a head, where we have 0 heads. So we have where you have 0 heads, there is only 1 point, which is tail. So the probability of getting a 0 is 1/8. Are you getting me?
Sir, request to come again there, sir.
Okay. Let us read the example again. We are tossing 3 coins. And I hope you remember the sample space for the 3 coins. Remember, it had 80 points. We have 80 points. We listed them. Head, 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 tail, head, tail, head, head, tail, tail, then tail, head, and so on. They were 80 points. Now, the problem we are talking about is that we are interested in recording the number of heads which we get after tossing 3 times. The number of heads which we get after tossing 3 times. So we are saying that you can toss 3 times and you don't get any head. You get 0 heads. So that is 1 point. You can toss 3 times and then within those 3 times there is only 1 head. You can toss 3 times. Within those 3 times, you get 2 heads. Or you can toss 3 times, and all the 3 times they are heads. Someone wants to say something, but the network is not let us get him. Hello? 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 Hello?
Yes, we are getting you, sir.
I hear some people, maybe they want to talk, but they are not, I'm not getting them. Okay, so let us go back. I was saying the example we have, we are considering tossing 3 coins. And you remember the sample space we are getting. We had 80 points. Now the question there is that let us record the heads we have within those 3. There is a possibility that you have 0 heads. There is a possibility that you have 1 head. There is a possibility that you have 2 heads. And there is also a possibility where you have 3 heads. So we are saying that the probability that you get 0 heads, I'm saying that that is 1/8. And I was explaining that it is because we have only 1 point, which is tail, tail, tail. That is the only point where we don't have any head. So it is only 1. So 1/8, we don't have heads. Then the probability of having 1 head. How many possibilities do we have where we have 1 head? Can you mention them where we have 1 head?
Possibilities where we have 1 head, they are 3.
Okay, so what are they?
We have head, tail, 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 head, then tail, head, tail.
Very good. So that is 3 out of 8. So the probability of getting one head is 3 out of 8. How about the probability of getting 2 heads? How many heads? How many times do we get 2 heads?
So still there are 3.
Okay, what are they?
We have head, head, tail. Head, tail, head. And then tail, head, head.
Okay, so there are also 3. How about the probability of getting 3 heads?
Probability of getting 3 heads. It is 1.
So that is 1 over 8. Is that right?
Yep.
So we have those probabilities there. Probability of 0 heads was 1 over 8. Probability of 1 head was 3 over 8. Probability of 2 heads is 3 over 8. Then the probabilities of 3 heads is 1 over 8. So each of the probabilities is non-negative, like you can see there is none of those probabilities which is less than 0. And then when you add up all those probabilities, 1 over 8 plus 3 over 8 plus 3 over 8, then plus 1 over 8, you get 1. You get a total of 1. So that is what we talk about. Okay? Because then someone can ask a question. This can say, what is the probability that at least you get to a head? What is the probability that you will at least get a head? So which answer can you give? Someone says you toss a coin 3 times. What is the probability that you will at least get a head?
So I think the probability of getting at least a head is 7 out of 8.
It should be out of 7 out of 8. Very good, because we leave only. The probability of not getting any head is 1 over 8. Therefore, when you subtract, I think you will get from 1. All of the other 7 possibilities, you can get a head. Okay? So that is 7 over 8. Very good. Yes, please. I think that is what we did at first. I think we did that one at first. I don't remember where it is. I think you see that one on the screen. We said that when you toss a coin 3 times, those are the possibilities you get. There are 8. Either a head, first toss is a head, second toss is a head, third toss is a head. So that is one possibility. Then we said you can get a head, the head and the tail. So that is what we are talking about. That is where we get all the 8 different possibilities. Is it okay? Okay. Okay, then when we talk about, I think we have already said that, now we are saying that if the probability space is finite and we have an equiprobable space, that means if chances of getting one is the same as getting the other, like for example, when we talk about these coins, the chances are the same. The chances are the same. So we say that that is an equiprobable space where all the sample points have got equal chances. Then the number of points in that sample, if it is n, if there are n, then we just say n times that probability. I think I can take you back to the first example where we are talking about days in a week. There are 7. And I said that if the possibilities of having, let me say, a lecture, it can happen on any day, there is no problem. Then we say that each day has got a possibility of having a lecture. So each day has got a probability of 1/7. But now that we look for the exact dates, we have only 3. So we take a 3 times 1/7, and that gave us 3/7 as the probability of having a mathematics lectures. So if the sample space is even, each point has got the same probability, then the number of points in the sample or in the event, you just multiply them by the probability of each point, and that will be the probability of that event. For example, here, we can say that the number of elements in the event over the number of elements in the total sample, that gives the probability of that event A. For example, in our case, we have 3 days, and the whole sample is 7 days. So the number of days in the sample, that is 3, over the number of days in the whole space, that which is 7. So the probability of having a mathematics lecture, then we can say that it is 3/7. Or we can say that the number of outcomes for event A over the total number of outcomes, that gives the probability of that event. Okay? Let us have an example. Let a card be selected from an ordinary deck of 52 cards. Let A be the event that the card is a spade, and B the event that the card is a face card. Okay? A face card, we said that they are the picture cards. Then A is the probability that is a spade. Can someone compute the probability of A? What is the probability of A? Hello? What is the probability of A?
So we are trying to add up.
No, you don't have to add up. But probability of A is very simple. No, the formula is saying number of elements in A over the total number of elements in the sample space. Now, A is the cards which are spades. Very good. So it is just 13 out of 52. That is 13 out of 52. Is that okay with everybody?
Yes, it is okay.
There wasn't a lot of calculating. How about, yes, please?
So now we are trying to refer to the other table.
Which table?
The one that shows the number of cards, the arrangements. So we are trying to, personally, I try to think, the origin.
You are trying to think about what?
About relate this one and what you have given us. Yeah, that's why I'm saying we are trying to add up.
No, because we said that every suite, you remember we said every suite is 13 cards. We have 13 clubs, 13 diamonds, 13 hearts, 13 spades. We said that.
Yes, sir.
And then we said that every suite has 3 picture cards. There is a K, a Q, and a J. And we remember we said that the total we have 12 picture cards. Is that right? That I think you will also remember that.
Yes. So now with this case of cards, when are jokers considered?
We said those ones are not playing cards. We don't include them. When we are talking about 52 cards,
Okay.
the jokers are not one of, they are not in that set of 52.
Okay, sir.
Okay. So we are now talking about this sorry. Yeah. Yeah, we are talking about the probability of B, where B is the event that you are picking a first card. A first card is the picture card. So what is that probability for a first card? Hello?
So first cards, the probability of first cards,
Yes, please.
16 out of 52.
Are they 16?
So you said the first cards are.
I said they are the picture cards. Those ones having bazungus. If you remember, I think I have been showing. Let me go back and show it again.
Hey, 1, 2, 3. Okay. Okay, sure. 1, 2, 3.
There are
Yes.
how many?
12 out of 52.
I think there are 12 out of 52. There are 12 out of 52. Then the intersection. Remember, we have 13 of them. Okay, because the question is that let us find out. Then the probability of A intersection B. Probability of A, we saw that there are 13 cards. They are all spades. Then the first cards we have seen 12, where three are spades, 3 are diamonds, 3 are hearts, and 3 are what? Okay. Okay, there are 3. Okay, we said there are 12.
Yes,
So what is the probability of A intersection B now? So what we are talking about, how many cards which are spades, and they are also picture cards.
Spade and picture cards.
I think that is what we mean by the intersection. Because the A, those are spades. B are picture cards. Then the intersection. That means we want to find the spades which are also picture cards.
That is 3 out of 52.
Very good. Okay, so that is those are the answers we have. The first was 13 out of 52 because we have 13 spades over the total number of cards, which is 52. That gives us 1/4. Then the probability of B, the first cards, we said they are 12 out of 52, and that gives us 3/13. Then the probability of A intersection B, meaning spades, and they are also picture cards, those are 3 out of 52. Is it clear now?
So it is clear.
Okay. So let us look at these theorems here. For every event, remember we said that the probability, I think it is just stating what we have already said. We said that the probability should not be negative. That means it is greater than 0. Then we said that the probability of the whole sample space, when you add up all the points, we have said that that is equal to 1. Okay? And we said that if the events are exclusive, that means if we don't have any intersection, the probability of A union B is equal to the probability of A plus the probability of B. Then the probability of A complement is 1 subtract the probability of A. I think you remember that one when we were trying to find out, like a case where we have at least one head when we toss 3 coins. We said that we just remove only 1 point which doesn't have a head, then all the others will be included. So you remember we had the 8. So when we removed the 1, we remained with the 7/8. So it is what they are saying here, that the complement is always 1 subtract the probability of that event. Okay, so it is the same thing here. I want you to note that theorem, especially that theorem number 7.4 down there. It is very important that the probability of A union B is equal to the probability of A plus the probability of B subtract the probability of A intersection B. Remember, we said that if the events are mutually exclusive, A intersection B is a 0. That's why in the previous formula we have seen the probability of A union B for exclusive events, it was only the probability A plus probability of B. But if the events are not exclusive, that means if we have some intersection, then we have probability of A plus probability of B subtract the probability of A intersection B. Is that okay? Okay. Very good. Let us look at this example here. Suppose a student is selected at random from 100 students, where 30 are taking mathematics, 20 are taking chemistry, and 10 are taking mathematics and chemistry. Find the probability P that the student is taking mathematics or chemistry. Now, if they say that they want you to find the probability that a student is taking math or chemistry, what do they want you to calculate? Okay. So they want you to calculate the probability of mathematics union chemistry. Okay. Now, what is the probability of mathematics? That is 30/100, which is like a 0.3. Okay. What is the probability of chemistry?
Tenth over 100.
10/100, which is 0.2. Very good. And what is the probability of math intersection chemistry? Because they are saying 10. That is
0.1.
0.1. Very good. Now we can calculate the probability of math union chemistry by using the formula which says what? Very good. So can you calculate that one? Very good. 0.4 or 4 over 10, which is 2.5. Is that right? So there we see probability of math is 3 over 10, that over 100, which is 3 over 10. Probability of chemistry is 20 over 100, which is 1 over 5. Probability of math and chemistry is equal to the probability of math intersection in chemistry, 10 over 100, which is 1 over 10. So by the principle, the addition principle, that means the probability of M union C is the probability of M plus probability of C subtract probability of M intersection C. And then we get 2.5, which is the same as 0.4. Is that okay?
It's okay. It's okay.
Okay. Now we have some questions here. Maybe we can try some. Determine the probability P of each event. An even number appears in the toss of a fair coin. What is that probability? A fair die. Sorry, it is a fair die. I think 3 over 6, which is 1 over 2. Okay, then find the probability that 1 or more heads appear when you toss 3 coins. 1 or more heads appear when you toss 3 coins.
So that is 7 out of 8, sir.
Very good. That is 7 over 8. Then a red marble appears when you draw 1 marble from a box containing 4 white, 3 red, and 5 blue. What is the probability that you will pick a red? The box has 4 white, 3 red, and 5 blue.
So may I try?
Yes, please.
I think here we have to first find a sample space. That is, we add 4 plus 3 plus 5, making a total of, I think, 13.
Are you sure? 4 plus 3 plus 5?
4 plus 3, that is 7. 12.
So that is 12. Very
Yeah,
good.
now that is the sample space. Now, the probability of picking a blue,
A red.
it will be 3 out of 12.
Okay, very good. So that will be 3 out of 12, which is when you cancel that one, reduce that one.
Get 1 out of 4. 1 out of 4.
It becomes 1 out of 4. Very good. Okay. I think this one we have already seen. A single card is drawn from a deck of 52. Find the probability that it is a first card. We said, what is that probability? The first card, we said, is the picture card. 12 out of 52. Very good. Then what is the probability of getting a heart? Very good. That is 13 out of 52. What is the probability of getting a first card and a heart? First card and a heart, that means what? Okay. So how many first cards are hearts?
Pardon, sir?
There are 3 first cards which are also hearts. Very good. So what is the probability of first cards? The probability of a first card and a heart? What is the probability? Out of 52, very good. Then probability of first card all heart. Probability of first card all a heart. What do they want there? The union, very good. So is it 13 out of 52? I didn't calculate. But anyway, we apply the formula, not so? That the probability of first union heart is equal to the probability of first plus the probability of heart, subtract the probability of first intersection heart, not so? Is that what we have done? The probability of first is 12 out of 52 plus the heart is 13 out of 52. Subtract 3 out of 52. What are you getting? Should be 22 out of 52. Very good. Which is 11 out of what? 26. Is that right? It should be 11 out of 26 when you reduce that. Okay. So 2 cards are drawn from an ordinary deck. Find the probability that both are spades. Two cards are drawn from an ordinary deck of 52. What is the probability that both are spades. No, it is not as simple as that. Now that one is not, it might be a bit hard, but let us, you see when you are drawing 3 spades, I think what we have to do here is to pick one at a time. So when you first pick, what is the probability of picking the first card, which is a spade? If suppose you are going to pick one card, what is the probability that it will be a spade? (13 out of 52). Very good. Now let us assume that we have picked that spade. So that is the probability, 13 out of 52, we have picked that spade. And we are going to pick another one. Now, how many spades are remaining now? Assuming that the first one was a spade which we picked. How many spades are remaining there now? So we are remaining with only 12 spades. And what is the total number of cards now? Okay, so what is the probability of picking a spade from the 51 cards? (12 out of 51). Very good. So, like we are going to see in a few minutes, or maybe the other lecture, we add up those probabilities. Sorry, we multiply those probabilities out, because you are like saying that you are having the first event and the next event.
The one.
Yes.
Yeah, then I think that is the probability, because already the number of cards reduced.
On that point, you are right, but now what you are forgetting
Yes.
So you are assuming that you picked a spade first
Yes.
and then a heart next.
Yes. But the
Okay.
number of hearts is still, it is 13. But
You,
the actual deck has reduced to 15.
you are right. You are right. But there is also another scenario that you picked a heart first, then a spade. That is also possible.
Yes. So it is
So-
vice versa, or I don't know.
So you
Whatever-
add up this time, because now the operation we are doing, we are saying that either you pick a spade first and a heart next, or you pick a heart first and a spade next. So if we are taking an or, it means we are going to do what? We are going to add those two probabilities. I don't know if you are getting me. They are the same probabilities, but it is like multiplying it times 2, because there is that possibility. Either you pick a spade first, heart next, or you pick heart first, then spade next. So we have those two possibilities, which means that you have to multiply by 2 to get the final answer. So what you got is correct, but we need to multiply that one by 2. Because what you got, you just assumed that you are picking a spade first.
Yes.
And the what? And the heart next. But I'm saying there is also a possibility that you are doing it the other way around. That you are picking a heart first, then a spade next. So it means, of course, they are going to be the same probabilities. So which means that you multiply them, that number which you get, that value which you get, you multiply it by 2. Is that fine?
It is fine, sir.
Very good. You know, we are going to see it more. We are going to see it more. Time is we are about to go, but we have a number of questions there. I think the notes are now appearing on V-Class. You can try to go through those other numbers. We have some other numbers, revision questions, which are following there. You can go through them. There are quite many. Is that right?
Yeah, it's fine, sir.
Okay, please. So let us meet again next week.
Okay, sir. Thanks a lot for your services.
Okay. Yes,
All right,
please.
thank you.
Well, I actually confess I don't know what they do.
So
I don't know what they do.
personally, there is a, there is a, when you were arranging that thing of the dice.
Mm,
So with the betting company behind there, when you are making a selection, what chances of winning, maybe in their database, there is that because now there are two teams playing, not so?
mhm.
So that team, it either has a win or draw. So that one you can arrange the number of goals in relation to the appearance of a dice. how two dice, when two dice are tossed. So it can be 1-1, 2-2, 2-3. So behind the database, I think they make such an arrangement so that when you score, the system, when you enter the results, the system triggers that chance. That chance appeared here. So that one has won. If you have not won, it will reflect a loss of that ticket. For me personally, I'm seeing that relation.
Okay, but you could.
Yes. Yes. Because I have ever made an arrangement of around up to 20 scores of goals. You understand? So that thing has appeared exactly the way I arranged that thing. So I think that thing is applicable in betting systems. Probability.
Okay, it is.
Yeah.
It is good if the real world. Otherwise, I wasn't aware. I don't know what is happening there.
So it appears. So
Okay.
for me, my view was, actually, I'm starting to thinking that I wish mathematics was the Bible.
Okay.
Because there's no deceiving. There's no deceiving.
Yeah, thing is when you go into it, because like I said last time,
yes,
most of these things like those people like manufacturing processors, like a processor, it carries out multiple operations, addition, subtraction, and what. So if someone is to design like a circuit, which we see, let me say, in a computer architecture, you have to think of all of these possibilities, such that whenever you put it into a computer, it considers like your input. Of course, it has to think of very many alternatives. Then you come up with what? You come up with an answer. So, colleague calling it like a Bible, it is a very good reference point. And like I said, I think it was yesterday. When you go deep in computer science itself, because the computer science itself is not like IT. I don't know if you are aware. IT, we are mostly in applications. Those things which you are going to use mostly when you go out. But here, this is a science. We are mostly interested in knowing how does the machine come up with the way the machine is behaving. So you have to know all the basics behind these operations. So that is what makes computer science a bit different from IT. Okay?
Thanks for giving us courage. Now, somehow we feel like giants.
Yes, exactly. Because that is what our job market dictates. From here, so long as you did the computing, you will apply for any job. Programmer, you will apply. Database administrator, you will apply. Networking, you will apply. But seriously speaking, there are some things which are mainly IT things, but they are not computer science. They are there. Like IT, you don't expect them to write so many programs. They are in database management, those things which are dealing with like monitoring or making the computer work, but they don't write programs. Okay? But for us in computer science, we have to write, actually, if you are a computer scientist, there is no way you can survive if you can't write code. And then the code has got a lot of mathematics behind. So there is no way you can program if you don't know mathematics.
So which means we go back to back house and maybe make some revision. Mm. Yep. I see.
They are very much related. So
now for us, we need more exposure. We don't have links, we don't have sources. And I remember faculty dean, actually, I've ever been in that office. They were like, you start now. By starting now, we are relying on what? We are relying on internet and so on. Yet we need some physical people to maybe help us guide us through.
It depends on what you are doing. It depends on what you are doing. The people find them if you are not interfacing with them. That means maybe if you don't have lectures with them, then maybe you will not have them. But I think we are trying to give support wherever it is necessary. I think we are trying.
Okay.
My advice is that whatever, and it applies actually to every discipline. For the moment, there is nothing that you study, because these people who design like a curriculum and they say such and such a group should know this and this. So I think we need to respect those people. There is a reason why they put like those modules there. So it wouldn't be good for someone to say, this one will not, you will not need this. Because whoever designed the curriculum, maybe he knew that at one time, maybe you will need to apply it somewhere. So my advice is that we get to learn whatever is there. The applicability will find its way when you have already known it.
So now for us, we feel we are even late.
Okay, you will get these things with the time.
Okay.
You will get it. Yeah.
And that's why for me, I always conclude saying, mathematics, this is it is the Bible. It could be a Bible actually, because it's full of facts. You can't deceive. 1 + 1, you can never get 4.
Yes.
So people who designed their Bible, who thought about the Bible could at least consider mathematics.
Right. Okay, good night, guys.
Good night. Good night. Emmanuel, yeah? Man, don't leave me. You are saying there are some nini you are 10 human from behind there. Now it has passed. They give us certificates.